All right. Um, so this presentation is a relatively short introduction to this project. That is it's a network architecture that brings hiCN into IPv6. I'm assuming not everyone is familiar with hiCN, so I'll give you also a very short introduction to hiCN and how this is made available into IPv6 in this project and in the software. So for those who have heard something about hiCN, you may have heard this as hiCN, like content-centric from Van Jacobson project at Park, or named data networking, which is another project currently funded essentially in the university through the NSF and Intel. But the whole idea is essentially dates back to almost 10 years ago when Van Jacobson launched this project at Park. And so more recently, like 2 years ago, Cisco acquired all hiCN IPR from Park. And then this is how we landed into this project, essentially, when this year we open sourced, 2 years ago, we open sourced the hiCN software. And this year we open source the hiCN software. But what is hiCN in the first place? So first of all, it's a network architecture. So you need to think about it as a layer 3 and layer 4 technology. And it's supposed to transport any kind of application. It's not about like content distribution, for instance. It can be used for real-time communications. And I show you a demo about WebRTC, for instance. It can be used for any kind of application, just like you may think about IP transporting any connected application. So what is what is the feature? The core component of hiCN is that it brings connectionless and location-independent communication into IP. And so this is the real advantage of it, as it enables a number of features that we'll see. The other component is that it's a intrinsically request-reply. You may think about TCP as a request-reply protocol where actually you send the data and then you get an acknowledgement after transmission of the data. In hiCN is essentially you flip around the communication semantics and you ask the data before you get the data from the network. The other component of the hiCN is location independent, means you get data from any place. So you can get the same data, it can be multi-sourced from different servers, and you don't want to take care about the location of this data. And so you get a number of security features to make this possible and secure, especially the authenticity of the source. Is this data coming from the actual producer of the data? So the producer, meaning the data owner that is sending data to me, and this is something that is built in the transport layer. So this is, for instance, something that is not available in TCP/IP. So in TCP, you don't have this feature. You essentially authenticate the endpoint. So when you have an authenticated connection from one point to another point, the only thing you know is that from this locator, so the IP address, to another location, you have a byte pipe, but the authentication of the data is essentially delegated to another layer, essentially the application layer. So the communication essentially moved the semantics from the what to the where. Well, from the where to the what, meaning that today even if the application is already today location independent, like I'm interested in data, I don't care where it is stored, you have a number of indirections today that at the end of the day you need a locator, which is an IP address. You need to open a connection to that locator and then move the data from one point to the location. So in this network architecture, it's the socket itself that can essentially connect to a location-independent name and not the locator. Now, this is, for instance, for those who are familiar with the IP multicast, this is what you do when you open a multicast channel. So you bind a connection, an application to a location-independent name, which is the IP multicast channel. So where, for instance, a TV channel is coming from. But it does not extend to all the other kind of communication semantics you can have today. And actually, multicast is something that is going away for this reason, because it cannot extend to all the other interactions. So hiCN brings a number of interactions that we actually have seen disappearing in the internet, which is many-to-many, which are essentially delegated into another layer. Anycast, multicast, mobility and multi-homing, which are most of the time solved in a different layer today. And the other feature is that you get redundancy elimination by design, because the socket binds to a location-independent name. And so if you have several sockets or connections or transactions, application transactions, that are looking for the same thing behind a given location-independent name, they're essentially asking the same thing, and the sender, which is stateless, is able to reply to several requests without opening several connections. So it's the unicast versus the many-to-many. And so some of the things we see later is that it helps a lot in many workloads where you have this many-to-many, you have a data source that is shared among several data consumers. And so group communication is one example. We'll see WebRTC demo later, the multicast case. But you also have the multi-source case where we typically associate to Anycast, where you can have the same data source that is essentially redundantly available in different locations. So let's go a little faster to the hiCN. So this is this very short introduction is about hiCN. So with the high-level principles. The hiCN is something that is available, that is in the software, is made available in IPv6, which means that the location-independent name I was mentioned before is an IPv6 number. It's an IPv6 address that is used similar to what we see, you may think about in multicast. But it extends to many other applications like RTP, HTTP. It essentially, so this name can bind to any kind of application data. Like anytime you have some data to share, you can use this location independent name, which is an IPv6 number. So how do we do this? As I said, hiCN is a layer 3 and layer 4 technology. The name prefix, what we call name prefix, is an IPv6 number, so it's 128 bits. And behind this number, you have essentially data source. We call it name prefix, even if it's from a locator perspective, it's a full address. It's not a locator prefix. And this is available in the layer 3 header, so just like a regular IPv6 header. Then we also need to identify, in a similar way, every single IP packet in the application stream. For instance, in the case of TCP, you have a locator, so you have an IP address. You also have a port to demultiplex at the server side, but essentially you have an IP, you have a locator to reach essentially the place where the data is stored. And then you have a byte pipe. So essentially, the byte pipe is meaningless for any other connection. So it's meaningful only for a given connection. So once you negotiate the offset, you can start essentially naming with the byte offset, so the sequence number, the meaningful pieces of data for the receiver of the data. And this is TCP. In the case of hiCN, we reuse essentially the sequence numbers to identify the chunks of data that are coming from a source. So this means that as soon as we concatenate the name prefix, so the location-independent name, the source data name, and the suffix, we obtain essentially an index which is unambiguous to index every single IP packet in a stream. So this can be used to share the same data among different data consumers. So let me go faster. I mentioned, so a core component of hiCN is the fact that every single transport layer transaction is request reply, meaning that similar to TCP, as I said, every single packet in the stream can be indexed by the concatenation of the prefix and the suffix. So essentially, using information that is stored in the header field, so the layer 3 header, so the IPv6 address, and the suffix, which is stored in the layer 4 header, you have this index, which is used to essentially forge a request for this data packet. And then this is how the network can reply. The network, well, in the first place, is the server side, where the socket is open, where the data is coming from. But in principle, any place where this piece of data is stored can be used to reply back a requester. We'll see later how. But you need to think about what we call interest packet. Is essentially a request packet, similar to a TCP acknowledgement, and the data packet where you find the actual payload. There is additional security data that we'll see later, but like a signature and more. But this is the core principle. So layer 3 packet format. So as I said, we have essentially two different PDUs: the request and the reply. The request is carrying the name prefix in the destination address field of the IP packet, while the reply will bring the name prefix in the source address field. Essentially, if you think about an end-to-end communication where you have just a data consumer and a data producer, the data consumer will have in the destination address field the name suffix, which is an IPv6 address, which can be routed using IGP in the network, similar to an Anycast address, to a given place where this data is available, or an intermediate place where this data is stored temporarily. While as soon as the first producer or an intermediate node that has this data, well, the reply available, the source in the request, the source address field is carrying the locator of the consumer socket, which will be used essentially to reply back the data to the right locator. Locator or multiple locators, because you can receive several requests for the same piece of data carrying different locators in the source address field of the request, and then reply back with the data by essentially replicating the reply to all of them. And IP routing, by using location-based routing, will essentially transfer the data back to all consumers. This is all you need now for the routing part. So which means that from a routing perspective, well, we can be long, but you have essentially two different namespaces at the same time, which are used unambiguously. One is the locator namespace, which is the namespace we use today. And for those who are familiar with Lisp, or also ILMP in a way, you have an additional namespace here, which is the location-independent namespace, which is encoded in the same way as the locator namespace, just like in Lisp. The difference being that in Lisp, you essentially have a separation of the two namespaces by topology. Like the locators are used inside the network, and the end user, end host identifiers are used only at the end host. While every single request carrying a location-independent name can essentially be routed using similar to Anycast everywhere in the network, from the edge to the core. So the layer 4 header for hiCN essentially is a new header, but for many reasons, we are using a TCP header. So essentially, we are hacking the TCP header, or for other backward compatibility reasons, we are also using a UDP header plus a TCP-like header. So we could have used the quick-like approach by essentially redefining a new header on top of UDP, which is essentially what we are doing for the second header you see in the slide. And probably in the future we'll do that. But for the time being, we essentially run for several reasons, we have a high hit ratio by using this approach. But the only thing you need to know right now is the layer 4 header is a regular application level, transport level header, which is carrying a segmentation information, which is now not anymore like in TCP a sequence number, but it's carrying a location-independent suffix. So it's not anymore a byte pipe. Can also be a byte pipe, but in general, you just need to know where it is located inside this header. Doesn't move anymore. All right. So I already mentioned about the forwarding path. So you need to think about an hiCN socket as a consumer side, which is, well, you can think about an hiCN socket as a unidirectional socket, one to receive data and one to send data. Then if you need to send and receive data at the same time, you essentially have both directions in the same place. But and this is different with respect to TCP or others. But essentially, you have a unidirectional socket. The consumer is reading, essentially send a request, and get replies from the network or a server. And the producer is just producing data, segmenting data, and making this data available in a memory so that any consumer can use to essentially fetch the data from the server or an intermediate node. So essentially, we have two different forwarding paths in the network. One is the request path, because they are forwarding in the network using location-independent names, so which is the data source name. But it's an IPv6 name, so it's an IPv6 address. So you can use IGP essentially to distribute these names through the network. The only difference is that once you have this name, you can use to essentially implement the hiCN semantics. And this is a pipeline, the router pipeline for the hiCN router for the request forwarding path, which is essentially an IPv6 pipeline where you have essentially the ingress with the packet parser in the first place, where you identify the required field. In an IPv6 array, well, in addition, you have a new data structure, which is the packet cache, that we use to cache temporarily the requests and the replies. We'll see why. But essentially, you have the packet parser, just like any other IP pipeline. And at the egress, you have you have an IPv6 fib. You have a load balancer, typically, that we call forwarding strategy. And then you have the egress. So the only operation you need to, so the reason why we have this additional packet cache is that because we want to reuse, essentially, as much as possible, the requests and the replies. If you can reuse a request, that means that you have several users asking for the same thing. And then the same reply can be stored for a short amount of time to satisfy several requests coming from different locators, so different consumers. And so this is the reason why we have this packet cache, which will be used also to implement the data, so the other pipeline, which is the data forwarding path. Well, in addition to the regular IP pipeline in the packet parser, we also need to locate the name suffix. And that's the only additional component. So because we need to be able to understand that if this data, this piece of data, this singular IP packet, data packet is already there. And that's it. So we can see more detail maybe tomorrow at the Cisco, at the FD.io booth. The other important pipeline is the data coming back to the consumers, which is not using anymore the IPv6 fib to reach the consumers. Not at this layer. Meaning that you still have the packet cache, but if the packet cache is storing different requests for the same thing, when you have the data coming back, then you can see that are essentially many different consumers that are asking for the same data, and you can recognize that because once you go through the packet parsers, you see that actually this name prefix plus suffix is actually available there by using an exact match lookup in the data cache. And then you find all the locators already there stored in the request. So essentially, the data packets are not routed by destination address, but they are label switched essentially by name, because the information they find in the packet cache behaves in a way that essentially you already know where to send the data back by essentially retrieving the locator of the request from the dependent interest in the packet cache. Then, of course, in the pipeline, this you have a locator. Then, if you want to route this packet into the network can be just an X hop, and the next hop can be a regular IP router. So we'll be using IPv6 lookups as well. Let me go faster to application support. So this is essentially most of the hiCN architecture for what concerns the layer 3. So layer 4, as you said, we have a consumer socket, we have a producer socket, but this can be for any kind of transport service. It can be real-time, can be TCP-like, video, MPEG dash, whatever. And this is going to be part of the different transport protocol implementation you can have in the software. You have at least 2 right now for real-time audio and video. Supporting RTP right now and or SRTP. We also already support HTTP, and especially we support HTTP for a kind of HTTP over multicast. When you have essentially several users, you want to broadcast or multicast video to several users, but instead of doing HTTP over multicast, you do HTTP over this special socket. Let me skip very quickly to a very short demo here. So this is an example where I show the current prototype where we are running a typical pipeline in HLS video distributions where we essentially have an origin server where you have an Nginx origin distributing different live channels on HLS with packaging following the typical HLS live streaming packaging. I think it was 2 seconds packaging. And then we're essentially comparing what happens when we have an ATS web cache, it's an Apache Traffic Server web cache, that is used in either TCP or an hiCN socket, the producer socket in this case, and when you have several users asking for different channels randomly following a given distribution, so there are more popular channels that are more frequently requested by users. We have 150 users asking for a group of, I think it was 150 different channels, right? In the case of HLS over TCP, you need to have as many TCP sockets open at the ATS cache as the number of users. So no matter if they watch the same channel, essentially the channels are distributed in unicast. And so the ATS cache has to manage as many sockets as the number of users connected to the web cache. In the case of the hiCN socket, we essentially have as many producer sockets as the number of active channels, which is, in this case, in average was 26. And so the load at the server is proportional to the number of active channels and not to the number of users that are connected to the web cache. And so this is what I meant when I mentioned at the beginning that it can help for different kind of work where too many matters. And we compare his CPU and memory usage at the web cache here. We are not reporting the kernel. So in the case of TCP, we're using the TCP kernel stack. And in the case of hiCN, we're using our own hiCN implementation using VPP. And this is essentially the CPU usage of the application, the ATS application. So we're not reporting the cost of the VPP core, a single VPP core, or the Linux kernel cost, which is not reported here. So the other application that I wanted to show here is WebRTC, where we have an integration of the hiCN sockets for RTP, SRTP essentially. And we're not replacing all the sockets with the hiCN sockets, but we're using hiCN sockets only for some media channels. Essentially, for those who are familiar with the WebRTC application, you essentially have a contribution channel, which is essentially all the users sending media to the media bridge. And then you have a distribution channel, which is essentially the media bridge sending to all the participants the active speakers, which is a subset of the participants. So essentially the main speaker plus the second most active speakers, like someone who was talking before the active speaker, and those who are essentially recycled in the main screen. And in this case, we're using hiCN. We are comparing regular WebRTC. So WebRTC here is running in the web browser. We're using the Jitsi open source application, including the video bridge. And we're using hiCN sockets for contribution and distribution channels. And while we're using for signaling and all the control part of WebRTC regular sockets. So everything related to DTLS and all the web part of WebRTC is unchanged. And so the comparison here is how far we can scale when we have a MIDI bridge that scales with the number of active channels and not the number of participants in the call. Because in the case of regular WebRTC, you need to have the media bridge similar to what we have in ATS before, as many open sockets as the number of participants in the call. And so the media bridge scales with the number of connected users and not with the number of shared information between the participants. Sorry. Let me go at the end of the video and stop here. Essentially, what we're showing is on the right-hand side, what happens when using hiCN. Oh, no, wait a second. Left-hand side is hiCN, right-hand side is regular WebRTC. When the number of participants is increased in two different ways. One is by having the video bridge, which is an application level forwarder. The video bridge is using now the VPP hiCN stack. The number of clients, the number of participants does not affect anymore the load at the media bridge because I don't care. Essentially, the distribution channel, well, the contribution channel is not anymore push. Essentially, the video bridge can decide which are the participant that has to contribute to the call. Essentially, if you are not talking, nobody's watching you, you don't send video and audio, essentially. And in the distribution channel, you send to all participants only the media that matters. So the 5 most active speakers and the main speakers. Well, there's also the simulcast part here, which is every single user is also sending a different video quality in the contribution channel, which means that you have to multiply the number of participants to the number of available qualities to your system. In the case of hiCN, we can go up to here in this case, to 1,000 different participants in a single call, because the number of, in this case, we essentially add an additional VPP router next to the video bridge, which means that you essentially, the network can assist the application in the distribution, in the contribution channel, and it's the network that will take about scaling with the information that exchange between the participants. And so the media bridge, the application, you can see in the upper plot, the load in terms of CPU scaled with the number of participants, so the number of sockets essentially is 5 or 6 plus times the number of video qualities. While in the case of the regular Jitsi video bridge, you need to keep all of them, the stateful information you have in the media bridge is it scales with the number of participants, even if they are not essentially sharing media with anyone in the call. So this is another example. I can have another, but I don't know more time. There's another one, an application we recently made based on using the RSocket implementation. But we can discuss about this probably tomorrow or at the booth. So a few words about the implementation status. So we open sourced in January. We are essentially keeping track. So we are in sync with the VPP release, as our server stack implementation is based on VPP. But we also support end clients, essentially all operating system, Windows 10, macOS, iOS 12, mobile devices, essentially. And so we have an additional server stack, which is implemented using sockets. So it's much lower than the one we get for the server side, but the server side essentially is devoted to implementations like ATS, more infrastructure support, or the video bridge you can have in WebRTC-like applications. The transport side, there's a lot of work in the transport for essentially implementing transport services, reliable and not reliable. As I mentioned, we have audio, video, and reliable transport. Different kind of congestion control for many reasons. The way we essentially interconnect, so we have a single transport library for both stacks, like the client and the server, to avoid to have essentially to implement transport services twice. And we interconnect the transport stack to VPP using MEMIF, a MEMIF-based, the MEMIF library. And this is it. Essentially, work in progress, essentially make it better from a software perspective. So it is getting better in performance and also supporting more applications. So we have in our to-do list gRPC, for instance, but also BitTorrent for other applications. And we have also all the part related to management and control. So we are currently using sysrepo, a sysrepo plugin to have netconfig, telemetry, and stuff like that, and services. Like the HTTP service for name provisioning, which is essentially the component you need in hiCN, which is, okay, I have my locators, I do a DHCP request, and I get a reply with populate locators into my interfaces. But how do I get the name prefixes into my application in the first place? And so this is where an additional service that you need to have, which is a network service. And I'm done. Any questions?